Hello everyone, I'm Norman Welberger and welcome to this series on the sociology of pure mathematics. Today we want to be looking at a historically important question. In fact, we want to go back through time to get a sense of the positioning of mathematics within other intellectual disciplines and the historical extent of that, which is typically much greater than it is from any of the other sciences. So when we're studying pure mathematics from a sociological or human point of view, we want to look at it in a number of different ways. But in particular, it's also important to look at it across time. So not just a snapshot of how things are today, but more of a historical context. And this is really interesting in terms of the evolution of mathematical thought and practice. So we want to get at some of these ideas today in the context of a very important question having to do with the infinity of primes and going back to Euclid. Mathematics is almost surely the oldest continuous scientific tradition, especially if we incorporate or include astronomy and surveying in mathematics generally. So astronomy has been very closely associated with mathematics from very early days, and surveying also as well. So historically, roughly, we can trace things the following way. Beginnings of civilization around ancient Egypt and Mesopotamia around 3000 BC, where we have our first mathematics definitely appearing. And then later the Greek period from around 600 BC to 300 AD, centered in the Mediterranean region, and then followed by Hindu, Islamic, Chinese developments, although aspects of the Chinese developments also go back earlier. Now, throughout most of history, mathematics can be associated with practical or applied problems. But there's also some aspects which are happening even in this earlier period, which are more like pure mathematics, characterized by abstraction, concern for logical structure, and maybe even a disinterest in some sense from sort of daily real life situations. Definitely kind of an abstract point of view. And that really arises strongly in Greek mathematics. And there are many famous names associated with this kind of thing. Euclid, Archimedes, Ptolemy, Apollonius, and so on, many other famous mathematicians. And today we're going to be talking about Euclid particularly because he perhaps most clearly embodies this pure point of view. Archimedes, also very practical, Ptolemy involved in the astronomy. So it's really Euclid that sort of sets the stage for what pure mathematics actually is. Euclid was a very important mathematician who lived around 300 BC in Alexandria, which is the important city founded by Alexander the Great at the mouth of the Nile River in present-day Egypt. He wrote a book called The Elements, which summarized a large part of the mathematics that was known at the time and systematized by him. It's a remarkable work consisting of 13 books on planar geometry, number theory, arithmetic, solid geometry, and it's certainly the foremost textbook of all time. It's important because it gives a logical, systematic orientation to mathematics focused on clear statements of facts called theorems or propositions and supported with proofs and constructions. And the logical structure that he laid out was a sort of a model for mathematics research and mathematics education since then, for more than 2,000 years. His constructions were dependent on the ruler and compass framework for planar geometry. That was important at that time. Now, there are some logical weaknesses for Euclid, which largely have been sort of widely acknowledged only relatively recently, maybe since the late 19th century. But most of the time, these were sort of not stressed too much. And the book was hugely influential. It sort of was almost like, if you wanted to study mathematics, you studied Euclid. And previous generations of mathematicians would have learnt, especially the earlier books on planar geometry, would have learnt every single proposition and memorized all the proofs, 1, 2, 3, 4, and so on. So it was really a dominant dominant aspect structure in mathematics education for thousands of years. And no other scientific discipline can point to anything like this. So the other sciences, physics, chemistry, biology, medicine, these are, relatively speaking, newcomers to the scene. Maybe their histories are 400 or 500 years old. But if you go back to the ancient Greek times and earlier, it's very hard to find knowledge in those disciplines then which would be relevant to a modern education now. But mathematics, it's very different. Even a modern student can learn a lot from the ancient Greeks, and in particular, Euclid. Sadly, however, the tide has turned in the last 100 years, in the 20th century. The importance of Euclid steadily decreased, and now Euclid is virtually ignored by the educational community. So it's really a dramatic shift that we've seen that's attendant with the diminishing role of geometry in mathematics. And that, of course, is, to my mind, a very unfortunate development, and we need to sort of return to the central importance of geometry. So I do want to stress the importance of this longevity of the discipline to a sociologist trying to understand the psychology of mathematicians. You have to appreciate that we are part of this very long tradition, and we see ourselves as, adding to this body of knowledge, so that the body of knowledge is constantly being added, more skins, layers to the onion. With science, it's a little bit different. In fact, it's very much different. In science, there is more of an aspiration to completely overthrow previous existing theories and to put into place new and better theories. So there's an important distinction to be made here from a sociological point of view about the psychology of mathematicians versus that of scientists. They are very close, but there's still a distinction, and that's something that we will be talking about more in this series. Okay, so today, to sort of show how Euclid actually thought about things, I want to actually have a good look at a very important theorem of his, which has been a mainstay of modern number theory, and in fact the way we think about numbers. And this has to do with prime numbers. So let me remind you, even you sociologists, that a prime number is a natural number, say p, which has the property that its only divisors are 1 and p. So it has no other divisors or factors. And the prime numbers start with 2, which is the only even prime number, and then they go 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, and they carry on. And roughly what happens is there's irregularity, but they slowly start thinning out in some reasonably regular way, but still predicting exactly what this pattern does is very, very difficult and has attracted huge interest in the history of mathematics. And part of the reason for that is this fundamental theorem of arithmetic, which is at the heart of our current arithmetic, which was already recognized by Euclid. It states that every natural number, say n, is actually a product of prime numbers. So n equals p1, p2, up to pk, uniquely up to rearrangement. So you can take these prime factors and rearrange them, but otherwise the factorization is unique. So for example, 60 is 2 times 2 times 3 times 5. So the prime 2 appears twice. That's allowed, but all of these constituents are prime numbers. 1001 happens to be 7 times 11 times 13. This rather big number, which is 10,023,000, okay, that turns out to have a factorization of 3 times 11 times 19 times 41 times 389. And this kind of factorization is, in some sense, full of mystery. It's very hard to predict, given a number, especially if it's a bigger number, what are its prime factors. In fact, maybe it might even be prime, in which case it only has itself as a prime factor. So this is a source of a lot of study and interest in mathematics. And so this is part of the reason why the prime numbers are intrinsically interesting. All mathematicians are interested in prime numbers. So I want to have a look at a very particular proposition of Euclid, which is a very, very famous one. And this is an opportunity for us to peer into the way the Greeks thought about numbers, how they presented their proofs, how they thought about things. And it's also a chance for us to look carefully at a very famous argument. So we're talking about Euclid's Proposition 20 in book number 9. And this is the statement. Prime numbers are more than any assigned multitude of prime numbers. That's kind of, old-fashioned terminology. What is he saying? He's saying that there's more prime numbers than in any multitude. So if you get together a bunch of prime numbers, okay, there they are, you've written them down, they're in a box. He's saying there's actually other prime numbers, at least one other prime number, which is not in your collection. Okay, so you can always extend any given collection of prime numbers. Now, these days, we say this in a very different way. We say that there are an infinite number of primes. Okay, that's usually how Euclid's theorem is presented. But Euclid did not say it that way. He said it in terms of being able to go beyond any given finite collection. So he never actually even talks about an infinite collection. And that's quite important because I think, the role of infinity, the usage of that particular term is a very key question that overshadows a lot of modern mathematics. So we need to be very sensitive about this, and we need to be interested in the historical usage here to position ourselves in this trajectory of mathematical thought extending more than 2,000 years. Now I'm going to actually show you his argument, and I'm taking this from David Joyce's wonderful work of putting Euclid on the internet. Okay, so if you want to read Euclid, you can do that on the internet. Go to David Joyce's site and you will be able to find all these propositions and be able to experience it directly. Okay, so here is what Euclid says, translated, of course, into English. Let A, B, and C be the assigned prime numbers. So he's actually arguing sort of by example. He's saying, suppose that there's only 3 prime numbers, and he's going to demonstrate that there's actually another prime number, okay? And the argument is such that it doesn't really depend on there being 3. Okay, but in the ancient Babylonian times, this was a very standard way of doing things, is to present arguments by looking at actual explicit examples. Okay, so sort of following that tradition. So we're assuming that we have 3 primes in our box, and their names are A, B, and C. I say that there are more prime numbers than A, B, and C. So that's the claim that Euclid is making, and he wants to now establish this claim. So how do you start? Take the least number, DE, measured by A, B, and C. Okay, so this requires some explanation. You have to appreciate that to the ancient Greeks, geometry was more fundamental than arithmetic, especially when it came to sort of abstract mathematics. So a number was really kind of an encoding of a line segment. The ancient Greeks thought about numbers as being segments. So maybe that's the number A, that's the number B, that's the number C. They're represented by segments on the page. And what are we talking about the least number here? The least number DE. So here's another segment. It's expressed this way, DE from here to here, which is measured by A, B, and C. What that means is that this is another number which is a multiple of both A, B, and C. So if we took A here, then maybe we could copy here once, twice, 3 times. Okay, so we could say that DE is 3 times A. And then we take B and say, okay, oh, it's 4 times B. And maybe it's 1, 2, 3, 4, 5, 6 times C. So DE is a segment which is a multiple of both A, B, and C. Now, in the modern approach, we would typically say, why don't we just take the product of these three things? That's one way of thinking about it, that this segment here represents the product of them. But it's expressed in this sort of geometrical language. And now we add the unit DF to DE. What does that mean? Well, DF is another line segment which is expressing the unit. So in our system of line segments, we're saying that this is representing 1. Okay, 1. And then any other natural number will be a multiple of that 1. So this is the starting unit. So if you got 2 of these together, you need to have 2. When you put 3 of them together, you have 3 represented as line segments. So we would say that you take the product of these 3 numbers, A, B, and C, represented by this segment, and then you add 1 to get this bigger segment, EF. Now, if you're a sociologist, maybe you don't like maths that much, or maybe it's not your cup of tea, and the idea of a proof is kind of scary. I want you to think about a proof as just an explanation that is particularly clear and correct, and can be followed. That's what an ideal kind of proof is. So a proof is nothing to be scared of. A proof is just an explanation of something. And that's what we're doing here. Euclid is explaining why we can find a 4th prime if we start with any 3. Okay, so we've done the construction. Now we've got this larger segment EF, which you can think of as being the product of the 3 original primes plus 1 more. And now he says, then EF is either prime or not. Okay. First, let it be prime. So he's considering these 2 cases. All right, so let's suppose that EF is prime. Well, then the prime numbers A, B, C, and EF have been found, which are more than A, B, and C. So he's saying that this EF is obviously bigger than A, B, and C, so it's different from A, B, and C. Then it will be a new prime number. And so now we have a bigger multitude. These 4 things that we have now is a collection of primes which is bigger than the collection that we started with. And that was, remember, the assertion that he's trying to demonstrate. Okay, so that's sort of one case. Now, next, let EF not be prime. So now we're considering the other possibility, that this big thing that we've created, the product of A, B, and C plus 1, it's not prime. Therefore, it is measured by some prime number G. Now he's using basically this fundamental theorem of arithmetic. He's saying, okay, we have some number. It's not prime, but it can be factored into prime numbers. Okay, so we're drawing upon a previous result that he's proven. So it's measured or divisible by at least some prime number, say G. So G now is a prime factor of this big number EF. I say G is not the same with any of the numbers A, B, and C. He's claiming now that this new prime factor, which actually doesn't have to be big, right? It could be a small factor, but it's not going to be any of A, B, and C. So if possible, let it be so. So let's suppose that this is not the case. So I'm just reminding you about the configuration. There's ED, that was like the product of the 3 numbers A, B, and C that we started with. And then there's this unit DF that we've tacked on. Okay, now we're assuming that G actually does coincide with one of A, B, and C. So now A, B, and C measure DE. Remember, this is the product of A, B, and C. So when he says measure, he means divides. Each of A, B, and C divides DE exactly into a natural number of copies. Now, if G is going to be one of these, then G also measures DE. but it also measures EF. Right? G is, by assumption, a divisor of EF. And if it divides EF and it divides ED, then it must divide the difference between these two, which is the unit DF. Therefore, G being a number, it also measures the remainder EF minus ED, which is the unit DF, which is absurd because DF is like 1. And this number G, this prime number G that we're getting, divides 1. Well, there aren't any numbers that divide 1, any prime numbers that divide 1. And so this is absurd. And our assumption was that G was actually one of A, B, and C. Therefore, G is not the same with one of the numbers A, B, and C. And it is prime, because we've said it was a prime factor of EF. So the numbers A, B, C, and G are all prime and are more than the assigned multitude of A, B, and C. In other words, we found a fourth prime from our original collection of 3. And that is Euclid's proof of the statement that these days is stated as there are an infinite number of primes. But I do want to emphasize that that's not the way Euclid stated it. You can see from the argument that's not the way he thought about it. He thought about it as if you have a finite collection, and probably that's even unnecessary to say finite collection. You'd have a collection of primes, then you can always find a bigger collection of primes. You can always find another prime which is not in the given collection. And the argument doesn't really depend on there being 3 of them here. If there were 4 or 5 or 27 original primes, then the argument would be essentially the same. So a very famous argument going back to 300 BC. So you can see that, yes, the ancient Greeks really accomplished some remarkable things. And this is one good example of it. In modern language, we would say this in somewhat different way. We would say that given a set of primes P1, P2 up to Pk, we want to show that there's at least one other prime. And the essence of the argument, arithmetically rather than with geometry of line segments, is first of all to form capital N, say, which is the product of the primes, P1 times P2 times all the way up to times Pk, and add 1. So that's the equivalent of this segment DF that we constructed. That was step 1. The second step is to apply the fundamental theorem of arithmetic to this number n and find a prime factor of it, say q. And then the third thing is to observe that this q cannot actually be any one of the pi's because it divides this product plus 1, and if it was one of these things, then it would also divide the difference, which is that 1. So the argument is exactly the same. So this is the more standard modern way that you would see this proof in a modern textbook on number theory. And now I want to be a little bit controversial and suggest that maybe not all is entirely well with this proof. And I want to introduce an idea which I think is quite instructive, an idea. It's the notion of a subordinate proof. So I claim that this is what we might call a subordinate proof. What do I mean by that? It means that it relies on external computations which are not necessarily possible. So it's not as if we've done all of the computations in front of us and that they are visible to the reader. Rather, we've said that you've got to go off and do certain things. In particular, these two things. You've got to do this thing and you've got to do this thing. You have to first form this product and add 1. Now you might say, well, that's seemingly pretty easy. And maybe it is. And then secondly, you have to find a prime factor of this number. Now that is not necessarily so easy. In fact, it's not necessarily easy at all. If you have a big number, then factoring it into primes, or even finding one prime factor of it, is a highly non-trivial problem, which gets increasingly complicated as the size of the number gets big. So the problem here is that these two steps, although they're happily done if the numbers involved are small, become increasingly difficult and eventually effectively impossible when the number of primes or the sizes of the primes starts getting large. So let me show you how this problematic aspect of this proof manifests itself. So you have to understand that we know a lot about prime numbers, yes, but there's a lot more that we don't understand. In particular, it's not easy for us to generate big prime numbers. And mathematicians have sort of been doing this sort of as a hobby on and off for hundreds of years, trying to find a bigger prime number than previously. The current record is this number here. It's a Mersenne prime, which is a power of 2 minus 1. Okay. In fact, most of the recent records in the last 20 years are all Mersenne primes. So this number here is prime. It's 2 to the, let's see, it's 82,589,933. That is also a prime number. It has to be a prime in order for the whole thing to be a prime. So this number minus 1 was found by computer using the great internet prime search, which is a collective effort of thousands of machines around the world. It was found in 2018. So that tells you something, that even though there's a lot of machines and a lot of people looking for primes, they are not so easy to find once you get to these reasonably big sizes. The record 10 years earlier was this number here, which was 2 to the 43,112,609 minus 1. And if you go back another 10 years, roughly when the GIPS search was initiated, the exponent was 3,021,377. So, of course, these numbers are getting big, sure, but they're not getting as big in a dramatic fashion that you might expect, okay? So it seems as if, we're struggling to get numbers which are, having these exponents which are a lot bigger than the previous ones. So let's focus our attention here with this question. Is there a prime bigger than 10 to the 10 to the 10? So 10 to the 10, that's like a 1 with 10 zeros. So that's a little bit bigger than this, but not that much. And okay, we're doing base 10 instead of base 2. But roughly, this is sort of, at least roughly comparable to this size here. It's bigger, but we could maybe hope that there will be a Mersenne prime found someday which is bigger than this. That's certainly not impossible. But what about proving that there is a prime bigger than this? Does Euclid's proof actually apply? This is a really great thing to think about, especially if you're an undergraduate or graduate student. Does the argument that he laid out work? So what do you actually have to do? Well, in order to find or to prove that there's a prime bigger than this, what you have to do is you have to take all the primes less than this, that's sort of like the existing set of primes, and prove that there is one more. Now you need to have all of those primes, but you just choose, say, half of them, then Euclid's proof is going to generate another prime, but it might still be less than this quantity. You want a prime that's bigger than this one. So to guarantee that, you should take all the primes less than this number. Now there's no way we can access that. That is so huge. We know a selective number of primes, but the vast majority of primes in this size we have no idea about. Okay? So it's completely impossible for us at this stage to take all the primes less than this. Even if we were able to do that, to take their product is now highly non-trivial. That would probably blow out, that the whole universe would probably be not big enough for our hard drive to be able to write down that big number n, especially then you have to add 1. Okay. So you got this humongous number, maybe it fits inside the universe, maybe not. But then you have to, in the next stage, you have to apply the factorization theorem. You have to find a prime factor of this thing. Okay, so you have to do a sieve or something or other, but you're going to be guaranteed that any prime that you find is not going to be in this range here. So the prime that you're going to find, if anything, is going to be mega huge. So roughly, so this is really a next to impossible task. You are just nowhere near being able to do this. So although Euclid's prescription, okay, works sort of in theory, actually it is running into this obstacle that the numbers get too big to actually fit inside our world. Okay, so the argument breaks down not necessarily just because our computing resources are not big enough, but because the universe that we live in is too small. And maybe here is sort of, touch and go. Maybe with quantum computer or something, some of these things could be overcome. All what you have to do is throw in another exponent up there, and then the whole question just blows out completely. Then quantum computers are not, no technology is going to be able to answer this question. At least with our current understanding of prime numbers, which has been gained by a lot of experience. So if someone miraculously finds some formula for prime numbers, people have been searching for this for thousands of years, no one's found it, and almost everyone believes that there isn't such a thing. But if someone did find such a thing, then maybe they could actually just write down some formula for some prime that's bigger than this. But I think the chances of that are less than 1%. That's probably very generous. The chance of being able to prove that you actually can write a prime bigger than that is absurdly small. It's essentially zero. So from my point of view, the statement that there are an infinite number of primes really bumps up against this problem of big numbers and that arithmetic breaks down with big numbers. It's not a true statement in my view. It's a fine statement as long as the range of arithmetic is relatively small and manageable, but in terms of the entire expanse of numbers, no. So this is an interesting sociological point. It raises all kinds of questions having to do with sociology of mathematics, and I hope you've enjoyed this brief foray into primes and Euclid. And you can sort of see that there's sociological aspects of this. There's a bigger picture having to look at the evolution of mathematics and pure mathematics, especially across time. I'm Norman Wahlberger. Thanks for listening.